In this episode, we will talk about emerging properties in unified multimodal pre-training. We're looking at how you train a single AI model on, well, different kinds of data, like text and images together,
Right.
and how that can lead to some really surprising new skills.
Exactly. It's like the model learns from reading books and looking at pictures and suddenly develops insights it wouldn't get from just one or the other.
Yeah, insights or even completely new abilities.
That's the core idea. And we're focusing specifically on these emerging properties.
Okay.
These are abilities that just sort of pop up, usually pretty late in the training process.
Things you didn't necessarily expect.
Precisely. They're not really there in the early stages, and you often can't predict them just by looking at how well the model seems to be learning basic stuff, like, its training loss.
It's those aha moments, but for the AI itself.
Kind of, yeah, like a sudden leap in capability.
So today we're diving into a specific paper that looks at this. It's on RLICL, identifier 2505.14683. It explores these properties in a new kind of unified model. And for you listening, maybe you're keeping up with AI, prepping for a meeting, or just really curious. We want to give you a good, solid understanding of these unexpected jumps.
Without getting totally bogged down in the super technical jargon.
But we want to highlight those key findings that make you think, didn't see that coming.
Okay, so where should we start? Maybe with the model itself.
Good idea. The model in the paper is called BAGEL, which stands for bottleneck-free architecture.
Right, and a big part of BAGEL is its architecture. It uses something called a mixture of transformer experts. Let's call it MOT.
MOT, okay.
Think of it like the model has different specialist teams inside it. One team is good with text, another with images, and the MOT system activates the right team or expert for the job at hand.
So it's selective.
Exactly, it's selective. And that's important because it stops the model from just becoming okay at everything too quickly. It allows these really specific advanced skills to develop later on.
Okay, so let's unpack that bottleneck-free part. You mentioned older models often had bottlenecks.
Yes. Many previous approaches, the paper mentions a few, like models 18, 56, 68, 72. In their references, they had these connectors between the part that, say, understands the input and the part that generates the output.
Like a narrow hallway between two big rooms.
That's a great analogy. It limits the flow. BAGEL aims to remove that restriction.
And what was the specific problem with those bottlenecks? What were they holding back?
Well, by removing them, BAGEL allows for much richer, more extensive interaction between understanding different kinds of data and generating it.
How does it do that technically?
It uses shared self-attention operations. So going back to that team analogy, it's like all the specialists can directly talk to and learn from each other constantly. There's no central choke point.
Ah, okay. So free-flowing communication.
Precisely. And this bottleneck-free design, this free flow, lets the model really effectively use huge amounts of training data and take advantage of very long training runs.
So the architecture itself doesn't become the limiting factor.
Exactly. The model's full potential can actually emerge. It's like giving that team unlimited resources and communication lines.
And to build this, they needed a strong foundation, right? What did they use?
They started with a powerful and, importantly, publicly available large language model, or LLM, specifically Qwen 2.5 large.
From the Qwen team. Why that one?
Well, it's known for strong performance, especially on language tags, obviously. And architecturally, it has a lot of the standard good stuff you see in modern LLMs.
Like what?
Things like RMS norm for stable learning, SWIGLU as the activation function, ROPE, that's rotary position embeddings for understanding word order, and GQA, grouped query attention, for more efficient processing. They also added something called QK norm.
QK norm.
Yeah, it's another normalization technique. It's become pretty common in models that generate images or video. Helps keep the training stable, especially at scale.
Okay, so a solid, well-established language model as the core.
That's the bedrock, yes. Then they built the multimodal parts on top.
Right. So how does BAGEL actually see? How does it handle images?
It does it differently depending on whether it's trying to understand an image or create one.
Makes sense. Let's start with understanding.
For understanding, it uses a vision transformer, a VIT, as an encoder. You can think of a VIT as breaking an image down into smaller pieces, like visual words or tokens that the AI can process.
And is this VIT trained from scratch?
No, they initialize it with cyclip2 SO100 millifore14. That's a powerful pre-trained model, already really good at pulling out visual features because it's seen tons of images.
So it starts with a good visual vocabulary.
Exactly. It works with images at a base resolution of 384 pixels, but they use techniques to handle larger images too, up to 980 by 980. They interpolate position embeddings, basically helping the model know where the visual tokens are, even in a bigger picture. And they also use something called native.
Navid.
Yeah, it helps the model handle images in their original shapes, their native aspect ratios, so you don't have to awkwardly crop or stretch everything to fit a square.
That sounds useful. And how does the visual info connect to the language part?
There's a connector, actually, a pretty simple one, just a two-layer multi-layer perceptron, or MLP. Its job is just to translate the features coming from the VIT into a format the LLM part can understand.
Okay, so VIT for understanding, MLP to connect. What about generating images, like text-to-image or sequences?
For generation, it uses a different component, a quantized variational autoencoder, or VAE.
VE, okay.
A VAE is trained on tons of images to learn a kind of compressed code for visual information. It learns to represent images efficiently.
And how is that used when BAGEL generates something? Like text, then an image, then more text.
Right. In that kind of interleaved generation, when the model is deciding on the next image or text token, it pays attention to the clean, uncompressed image representations from the VAE and also the visual features from the VT of any images that came before it.
But not the compressed VAE codes themselves.
Not the noisy, intermediate VAE tokens used during the generation process itself. No, it attends to the clean versions of past images.
Got it. The paper also mentioned something called diffusion forcing for generating multiple images in a row. What's that about?
Oh, yes, diffusion forcing. That's a technique specifically for generating sequences of images. The idea is you add a bit of random noise, different amounts for different steps of the process.
Why add noise?
When generating the next image in a sequence, the model looks at the noisy versions of the images that came just before it. This helps it learn the flow, the connection between frames, making the sequence more coherent, like a smooth little video clip.
Interesting, so it learns temporal consistency that way.
Exactly. And to boost consistency even more, especially between images that are close together, they sometimes group consecutive images.
Group them.
Yeah, maybe groups of 2 or 3 images. Within that small group, all the image tokens can fully interact using attention, and they all share the same noise level. It encourages visual similarity within that sort burst.
So the frames in a short sequence don't suddenly jump or look totally unrelated.
Precisely. The paper also mentions using generalized causal attention. They implemented it with something called PyTorch flex attention.
Is that just a technical detail?
Well, it's an efficient implementation. Apparently, it speeds things up quite a bit, maybe doubles the speed. And importantly, during inference, when you're actually using the model to generate stuff, it allows the model to cache or store the key value pairs from previous steps.
The KV cache, right?
Right, but it only caches the clean VAE and VIT tokens. This makes generating long sequences much faster because you don't have to recompute everything constantly. And once an image is fully generated, the clean version replaces any noisy intermediate tokens in the cache.
Okay, one more technical bit they mentioned. Classifier-free guidance during inference. What's the goal there?
Classifier-free guidance, or CFG, is a common technique now to improve generation quality and control. During generation, the model essentially gets 2 versions of the prompt, the real one and an empty or generic one.
Why?
By comparing the model's prediction for both, you can sort of push the generation away from the generic output and towards the specific prompt. In BAGEL's case, during interleaved generation, they also randomly drop out some of the conditioning information.
Drop out, like ignore parts of the input.
Yeah, randomly. Like maybe ignore the text prompt 10% of the time, or the VIT image features 50% of the time, or the previous clean VAE tokens 10% of the time.
Why would you ignore the input?
It sounds counterintuitive, but it forces the model to rely more strongly on the cues it does have. It can lead to more diverse results and often improves how well the output actually follows the remaining instructions. Figure 15 in the paper shows this whole generalized attention setup.
Okay, that's a really detailed look at the architecture. BAGEL sounds complex, but thoughtfully designed. Now let's talk about the training data, it sounds like. A lot.
Oh, it's immense. Table 1 in the paper lays out the numbers. Just for text, it saw 400 million samples, about 0.4 trillion tokens.
Trillion with a T.
For understanding image-text pairs, 500 million examples, half a trillion tokens. For generating image-text pairs, way more, 1.6 billion examples, that's 2.6 trillion tokens.
Wow.
But the really interesting part, maybe, is the interleaved data sequences with both text and visuals mixed together.
Right, like web pages or videos.
Exactly. For understanding that kind of data, 100 million examples, another half trillion tokens. And for generating interleaved sequences, they used video data, 45 million samples, 0.7 trillion tokens, and web data, 20 million samples, 0.4 trillion tokens.
The scale is just staggering, but it's the diversity too, right? Especially that interleaved data from videos and the web. Why is that considered so important?
Well, think about video data. The paper points out it's incredibly rich. It's not just static images. You get world knowledge, you see how things change over time, how objects look from different angles, consistency of identity, complex motion.
Yeah, the real world isn't static.
Exactly. So training on video is really effective for learning things relevant to, say, editing an image based on context, or understanding spatial relationships for navigation, maybe even manipulating 3D objects.
Where did they get the video data?
Public online sources, plus a couple of specific open source data sets. One called Koala 36M, which has lots of instructional interaction heavy stuff, and another called MVIMGNet 2.0, focused on objects from multiple viewpoints.
So it's the dynamic, contextual nature of video that helps unlock some of these advanced skills.
That seems to be the hypothesis, yeah. That dynamic element is key.
And I imagine getting good video data isn't easy. Did they have to clean it up?
Oh, absolutely. They used a pretty rigorous filtering process, similar to what was done for a text-to-video model called T2V.
What did that involve?
Things like splitting long videos into shorter clips, cropping frames, automatically filtering out stuff like black borders, logos, burnt-in text. Checking for minimum length, resolution, visual clarity, how stable the motion is, and importantly, deduplication.
Making sure they don't just train on the same clip thousands of times.
Right. They used CLIP, that's contrastive language image pre-training, to find and remove clips that were visually too similar. Ensures diversity.
Okay, that makes sense for video. What about the web data? How did they turn messy web pages into useful training sequences?
That was also quite a process. They started with a big text corpus called omnicorpus, and then applied a two-stage filtering and captioning approach. Figure 4b in the paper shows this.
2 stages.
First, a course topic selection using website metadata. Then, a smaller vision language model, a VLM, helped pick out relevant documents within those topics.
So narrowing it down.
Right. Then they used an LLM to trim the documents, removing unrelated headers, footers, ads, that kind of thing.
And the images on the pages.
Filtered those too. Removed UI elements, low-res or blurry images, images with too much text. They checked relevance using CLIP again, making sure the image actually related to the nearby text. And they aimed for documents with a decent number of images, like 3 to 8 per document.
To get that rich multimodal context.
Exactly. And finally, they generated or rewrote captions for the images, sometimes using BLIP2, another VLM, or sometimes using an LLM to summarize long text between images, making sure the text clearly grounded the image it was next to.
That sounds like a massive data engineering effort.
It really does. The result was 20 million of these structured, interleaved web documents, a huge source of contextual, multimodal data.
The paper also mentions they generated some text-to-image data themselves. Why do that when they already had so much?
That was for a specific goal, encouraging more reasoned image generation.
Reason generation.
Yeah. They started with short, maybe ambiguous prompts. Then they used a big LLM, Qwen 2.572B, to elaborate on these prompts, adding step-by-step reasoning based on some initial guidance.
So the LLM explained how it would get to the final image.
Sort of, yeah. It generated a more detailed prompt and the reasoning trace. Then they fed that detailed prompt into an image generator called FLUX.1 dev to make the image.
And the training data was the whole package. Query, reasoning, image.
Exactly. A triplet original query, the reasoning and detailed prompt, and the final image. The idea is to teach the model to base its generation on a more explicit chain of thought, potentially leading to more complex and accurate images.
That's clever. And with all these different data types, text, pairs, video, web, generated T2I, how did they balance them during training? Did they just mix everything together equally?
No, they actually adjusted the mix over time. Table 3 shows the data sampling ratios at different points in training measured in trillions of tokens processed, like 0T, 1T, 2T, 3T.
So the recipe changed as the model learned.
Yeah. You can see the proportions shift, maybe more focus on basic pairs early on, then ramping up the interleaved video and web data later.
Why do that?
It lets you strategically guide the learning, emphasize foundational skills first, then push towards more complex integrated abilities once the basics are there. It might be more efficient, help these sophisticated skills emerge faster.
Okay, architecture, data. Now for the really fascinating part, the emerging properties. How does the paper define an emerging property in this context? What makes it different from just getting better at something?
Right, so in this work, an emerging property is a capability that's basically missing in the early training stages, but then appears, often quite suddenly, later on.
Like flipping a switch.
Almost, yeah.
Yeah.
It's often a qualitative shift. The model can fundamentally do something new. And crucially, you often can't predict it just by watching the standard training loss go down.
So the loss might be improving steadily, but then bam, a new skill appears.
Exactly. The loss might show gradual improvement on existing tasks, but these properties are more like sudden jumps into new territory, a qualitative change, not just quantitative improvement.
So how do they actually spot these moments? How do they measure or observe this emergence in BAGEL?
They were pretty systematic about it. They evaluated the model's performance on a whole range of different tasks, using checkpoints saved throughout the training process.
What kinds of tasks?
For general understanding, they used average scores on standard VLM benchmarks. For generation, they used something called the GenEval score. And for reasoning both simple and complex, they used a score called JITIT, and a new benchmark they introduced called Intelligent Bench.
Intelligent bench, designed for harder reasoning tasks.
Exactly. Tasks that need more complex, multi-step thinking across text and images. By tracking performance on all these benchmarks across the training history, they could pinpoint when different abilities started to show up.
And what do they find? Did things emerge at different times? Figure 7 in the paper shows this, right?
Yes, figure 7 is key here. They found some really interesting patterns. Basic stuff like standard multimodal understanding and image generation benchmarks tended to improve quickly and then level off relatively early.
How?
They reached 85% of their peak performance, around 0.18 trillion tokens for understanding and 0.68 trillion tokens for generation. So pretty fast, relatively speaking.
Okay. What about more complex tasks?
That's where it gets interesting. Tasks that need both understanding and generation working together, like editing an image based on instructions, those improved much more slowly.
Slower convergence.
Much slower. It took about 2.64 trillion tokens for editing performance to reach that same 85% mark. Suggests combining those basic skills is significantly harder, needs way more training.
That makes sense. Editing requires understanding the request and the image, then generating a precise change. But they also mentioned intelligent editing emerging even later. What's that?
Yeah, intelligent editing refers to editing tasks that require even more sophisticated reasoning, maybe generating completely new things based on the instruction, not just modifying what's there.
And when did that show up?
That emerged significantly later. It took around 3.61 trillion tokens to hit 85% performance on those tasks.
Wow, much later.
Right. This really strongly suggests that as training scales up, the model isn't just getting incrementally better, it's developing qualitatively new, more advanced reasoning abilities that build on top of the earlier skills.
The paper also shows some actual image examples in Figure 8. What did those reveal qualitatively?
Those are quite telling. They observed that the general quality of generated images was already pretty decent before 1.5 trillion tokens. It got a bit better later, especially after they started training at higher resolution around 3.0 trillion tokens, but the big jump in quality was earlier.
Okay, so image quality improved early. What emerged later?
Something seemingly quite basic. The ability to accurately render text within an image, like spelling hello or bagel correctly.
Maybe later.
Much later, somewhere between 1.5 trillion and 4.5 trillion tokens.
That's surprising. You'd think spelling would be easier than making a photorealistic scene.
Right. It suggests that even seemingly simple skills might require a really deep understanding and integration across modalities, needing a massive amount of data to get right within such a complex system.
And Figure 9 showed emergence in those intelligent editing tasks. How did the model's behavior change there?
That was also very clear. Before about 3.5 trillion tokens, if you gave the model a complex editing instruction, it often just kind of ignored the hard part. It might reproduce the input image with only tiny changes.
So it couldn't really do the reasoning required.
Seemed like it, yeah. But after that 3.5 trillion token mark, its behavior changed qualitatively. It started making edits that showed clear reasoning, edits that were semantically appropriate and actually followed the complex instruction.
Generating new things, making significant changes.
Exactly. A real shift from just copying to actually reasoning and creating based on the prompt. It strongly backs up the idea that these complex reasoning abilities emerge late.
So the picture that emerges, sorry for the pun, is that the model first learns the building blocks, understanding images, generating images. But it's only after truly massive training that these separate skills start to synergize, leading to more complex compositional reasoning across modalities.
That's exactly the argument. And the paper stresses these aren't just cherry-picked anecdotes. They're backed by performance on public benchmarks, plus their new intelligent bench, and shown clearly in the qualitative examples.
And the architecture is key to this synergy.
They argue yes. That shared self-attention in the unified transformer, the bottleneck-free design, is what allows the model to explore understanding and generation jointly. That joint exploration, powered by scale, leads to this whole spectrum of emergent abilities.
It's a fascinating look at how learning happens in these huge models. Okay, so BAGEL shows these emerging properties. How does it actually stack up against other state-of-the-art models? They did benchmark comparisons, right?
They did. A whole battery of benchmarks. For understanding, they used common ones like MME, MMBench, MMVet, MMMU, MathVista, MMVP, a lot of acronyms.
The usual suspects for multimodal understanding.
Right. For text-to-image generation, they use Genival and a newer one called WISE, plus qualitative examples. And for editing, they use their own Jedit bench.
So how did BAGEL do on understanding compared to others?
Table 4 shows the results. BAGEL, when comparing models with a similar number of active parameters, around 7 billion for BAGEL, generally did very well. It outperformed other unified models like Janus Pro on some tough benchmarks like MMMU and MMVet.
Better than other models trying to do everything at once.
In many cases, yes. They also noted that one competitor, MetaQuery XL, uses a frozen backbone, which might limit it. Interestingly, BAGEL was also competitive with models specialized just for visual understanding, like Qwen 2.5 VL or Intern VL 2.5.
So being unified didn't hurt its understanding skills too much.
It seems the mode architecture did a good job of managing the different tasks, mitigating that potential conflict you might expect between, say, understanding and generation.
What about generating images, text to image?
The excerpt we have doesn't give hard numbers for Genival or WISE, but it mentions qualitative comparisons in Figure 10. These likely show BAGEL producing high-quality, relevant images, holding its own against top-generation models.
Okay. And image editing. How did it do on their Jedit bench?
Table 7 shows that. It achieved competitive results against both open-source models and even some proprietary ones. They used GPT-4 to evaluate the edits on metrics like semantic consistency, perceptual quality, overall quality.
So judged by another powerful AI.
Right. And BAGEL performed strongly there too, showing it can effectively combine understanding the instruction and generating the edited image.
Yeah. So overall, a strong showing across the board. But no model is perfect. Did they show any areas where BAGEL still struggles?
Yes, they were transparent about that in Figure 17. They showed some failure cases.
Like what?
Challenges remain in a few areas: generating specific intellectual property, rendering really complex text accurately, getting intricate human poses just right, generating multiple different objects correctly from one prompt, or doing complex object swaps while keeping everything else consistent. These are tough, nuanced tasks.
And other models struggle there too.
Yeah, they note that even models like Gemini 2.0 have trouble with these. Interestingly, they mention OpenAI's GPT-4o seems to handle these specific tricky cases a bit more reliably at the moment.
So room for improvement. How might BAGEL get better at those things?
The paper suggests a few paths. More data, especially data-rich and the kinds of things it struggles with, like complex text and images, maybe just making the model even bigger, or using reinforcement learning from human feedback, RLHF, as a final tuning step.
RLHF to align it better with what humans judge as a good output.
Exactly, fine-tuning based on human preferences.
Okay, let's try to wrap this up. If you had to boil it down, what's the single biggest takeaway from this deep dive into a BAGEL and emerging properties?
I think the core message is that unified multimodal pre-training, especially with these carefully designed architectures like BAGEL's bottleneck-free multi, really benefits from scale in ways that aren't just linear improvements. Meaning, as you scale up the training, you don't just get better versions of the same skills, you get fundamentally new skills emerging. There seems to be this synergy between understanding and generation that unlocks more complex abilities like sophisticated editing, long context reasoning across modalities, things that weren't explicitly trained for but arise from the combination and the scale.
And crucially, these aren't always obvious just from watching the training loss go down.
Absolutely critical point. These qualitative shifts, these sudden emergences, highlight why we need to evaluate these massive models broadly across many different kinds of tasks and throughout their training. Standard metrics don't tell the whole story.
Which definitely raises some big questions for the future of AI, doesn't it?
It really does. What other capabilities are lurking, waiting to emerge as we build even larger models and feed them even more diverse data? Can we get better at predicting or even guiding this emergence?
Yeah, can we harness it?
Yeah.
And maybe even, I don't know, does watching intelligence emerge in these artificial systems give us any clues about how intelligence arises more generally?
That's the really profound question, isn't it? Could studying these emergent phenomena in AI provide a new lens, a different way to think about the development of intelligence itself, whether it's artificial or biological? It's certainly a provocative thought to end on.